See, in the last class, what we managed to do was develop this effective mass picture for semiconductor heterostructures and nanostructures. And we showed that if we have a single dopant atom in a semiconductor crystal, then that problem is in the effective mass theory becomes equivalent to a hydrogen atom problem. And then you can solve it and find out the activation energy of the dopant, be it an acceptor or a donor. And these were kind of the results we ended up with, that if I put a dopant atom, then these are the possible energies allowed for that extra electron that came with the donor atom. So just to kind of look at it, if you want to map it, then if we put a hydrogen atom in vacuum, then the electron sees the proton of the hydrogen atom, right, and gets attracted to it with Coulomb attraction. And then it has all these energies, eigenvalues that a Schrodinger equation gives you. In the same way, when we put a dopant atom, for example, the dopant atom has one extra electron than what is needed. Silicon is replacing gallium here. Therefore, it has one extra electron. And now the whole crystal and the energies, the band structure of the crystal is like vacuum for this extra electron now. Right? So that's the analogy here. And therefore, it also sees hydrogen atom-like energies, except the conduction band offers a continuum of states, valence band, continuum of states. So these are the states inside the gap now, just below the conduction band. Just like an electron, if it sees the proton, it gets attracted to it. So the ionization energy is negative. Right? So this is in the same way the donor electron sees these energies. So that was the and if I look at the donor atom, the conduction band around it, this is greatly exaggerated. Will look something like that: valence band, conduction band, and the electron, the envelope function is going to look something like this. Right? So that would be your envelope function C of R, which for the hydrogen atom, if we look at the ground state, goes as minus R over the Bohr radius. But for this donor here, this Bohr radius gets slightly modified, and much larger than the 5 angstrom Bohr radius of a hydrogen atom, because it's sitting in a dielectric material with a dielectric constant that's 10 times that of vacuum. Permittivity 10 times that of vacuum, and the effective mass ME over, this is the normal mass, that's 0.1, so 100 times longer radius. So that's your envelope function that we got from the effective mass equation, but the total wave function really is the envelope function times this block function, and the block function is actually a periodic function. So meaning if the conduction band is made of s orbitals, then every unit cell has this block function which is repeating, right? And so the net wave function is the product of the two. So in other words, you can imagine how it will so it will kind of oscillate like that, but that will be the envelope of that function. So it will look something like that, the total wave function, right? So in other words, what we have done is we have managed to now localize that electron kind of nearby this dopant, and by introducing this envelope function, which is clearly composed of some CKs times remember we kind of, this is composed, it is not just one wave. Many waves have come together to have a localized state here, right? So with different Ks, right? So if you remember, this is really this part, the envelope function is just that. So it's kind of many Ks are involved here. In the very same way, if I want to localize electrons in a quantum dot, quantum well, there will be various Ks that will come together to give you the envelope function for various situations. So let's look at a few things that that follow from this sort of a picture. And in terms of where to read up this material, so this I think we are starting out with quite a few semiconductor heterostructures, and we'll fully at the end of the class also have a demonstration of such a quantum well heterostructure and what you can do with it. So so please read up this part of the handouts, and it has in detail all the stuff I'm talking about right now. So but I'll not go through the slides at this point. So let's use the board. So the general picture would be we will identify in various low-dimensional structures, nanostructures, what is this combination that gives you an electron state that may be in a ground state of a quantum well, or some things like that. So we kind of and want to start using it, the effective mass theorem, for these structures now. Okay. So. So the next example I want to give you is from the perspective of transport. Let's look at a one-dimensional situation where the conduction band is really not flat, but it's bending like that. It's very, most devices will have that, like a PN diode will have it. If you have P-type on this side and N-type on this side, the Fermi level is uniform. Conduction band is pulled down in the N-type, and the valence band is pulled up in the P-type, and you will have a situation like that, right? The valence band, and the gap is constant in a so and that's Fermi level. So P-type and N-type, and these are all filled states here. Valence band, that's conduction band, and let's say we want to ask a question that if I have an electron going over here, how do I track its motion, the current it carries, and all that sort of thing? We have already done this for quite a few situations. The free electron, a block state, a pure block state, we can write down the expression for the current, right? But here it's slightly different because things are changing in space. Things are changing in space here, right? So as you can imagine, as the electron starts out here, it has a very long wavelength because its kinetic energy in this band is low. But as you go across, it kind of accumulates. The wavelengths become shorter and shorter because its kinetic energy is increasing, right, as you move, right? So this is kind of the. So if you want to handle this situation, then we immediately realize my potential is changing in space, right? The potential energy or the minima. And I had alluded to this problem, to this situation in the last class as well. So here you can again write down your effective mass equation. And maybe you can tell me, how do I write effective mass equation for this situation? I'm tracking this electron, and I want to find the wave function for that electron at any point x here. So how do I do that? So effective mass equation is basically the Schrodinger equation, except there are small tweaks to it, right? So how do I write it? Schrodinger equation, so h squared by 2. Right. So now if it's in the conduction band, I choose the conduction band effective mass. Right? And in general, this effective mass may also change in general, because I can have one material here and I can put in a quantum well, and the effective mass would be different for that material. So that can also change. Let's look at a situation where I don't do that. In fact, the demo we'll do in the class today is where you will have a quantum well here, and we're going to push electrons in and holes in, and it's going to emit light. So we're going to look at that demo. But let's look at a situation where you don't have that situation, just a homojunction or a homogeneous material, but homogeneous band gap, but different doping. Okay? So, and then d2 by dx squared. Remember, essentially, the whole game in effective mass is replace k with minus I d by dx. That's kind of if you know the band structure of the electron in this material. If the band structure is E of k, is conduction band edge plus h squared k squared by twice the effective mass of the conduction band. Then all I'm doing is taking this k and replacing it with minus I d by dx, so I get a minus sign a double derivative, right? And then of which function? The function is actually not the total wave function, but the envelope function, just the envelope function. The block function cancels out on both sides, remember. So we're applying it now. Plus EC of x times C of x is equal to the energies allowed times C of x. So that's your modified Schrodinger equation. My potential minimum is here, right? This is the potential V term of Schrodinger. And that's the kinetic term. Right. So now this is, you can write this again as, rearrange it a little bit and write it as 2m star c over h bar square. And on the right side, I get EC of x minus E times C of x, right? And if you notice this now, we can write this as some function q of x. This is, we had written down the most general solution for it in this approximation form called the WKB approximation, right? In general, if you can see that if the EC minus E is positive, meaning energy was lower, if the energy was lower, then it's a evanescent state. It's in the gap now, right? And in which case you have double derivative is proportional to itself with a plus sign, so it must have decay or growth, right? Does that make sense? Of exponential. But if this energy is larger, meaning this term is negative, E minus EC is positive. So this term becomes negative, then you have a complex exponential. This is the oscillating function now. Except the wavelength or the wave vector is changing with x, right? It's not constant. So the most general solution for that is the WKB solution for a smoothly varying function, and I think this qualifies in this picture as a smoothly varying function. It's some constant, let's write maybe some constant C naught times e to the power any point you want to start from. Okay, so this is kind of the solution. This is the WKB solution for any differential equation. Double derivative is a function of x times the wave function. And from here you can kind of now see right away that you can take this term as q of x, replace it here, replace it there, and get your wave function at any point. You get your envelope function at any point as you move along. So, yeah. And you can do quite a few more things. For example, you can write down that. So if you notice this, this quantity is really kind of a wave vector at any point squared. That's what that is really. The wave vector k, 2 pi by the wavelength squared, right? So and if it is imaginary, then it's that. If it's oscillating function, you get a minus sign and all that. But the amplitude of this is wave vector squared. So, yeah.
The integral from a to x, is a just an arbitrary value? Like, can you assign it to 0, or is that the lattice constant?
Right. So actually, a is that kind of is your boundary condition here. Meaning, what we are really writing is the ratio of C of x divided by C of a. So this is really C of a. So. And you can start from anywhere and find the wave function here, and the constant will get modified based on where you choose your a. So one way to look at it is we are something like that. Let's say. So, but I'm not writing it that way. So just you can do it much more exactly. This is the a is a point which is outside of things. For example, if things have reached flat band here, you choose it here. Where things are not changing anymore. So, yeah. And what you can do here is you can show now that if I have a non-evanescent state, if the states are in the band, then it will go as e to the power I, k of x over square root of k of x. That's what it's going to look like. Where k of x is the 2m star c over h square e minus EC of x square root is equal to k of x. Okay. So you can show that very easily in a couple of steps here. And this is kind of a nice function because you can use now to find out what is the current c of x. Okay. So using this, you can write down what is the current, what is velocity, all kinds of other things with it, and plot it. That's one of the things you notice is if you take mod c squared for a non-evanescent state, what you will get is a const c naught squared, e to the power i's will go away, but you get it's divided by k of x, which is the wave vector of k of x. And if I go in and say that what is my current flowing, at any point here, 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 one of the things that whatever current is carried by the electron at this point will be exactly equal to this point, will be exactly equal to this point if there are no reflections. If there's no reflection, then whatever probability of the state is being carried across here must be equal to its current continuity. It's kind of continuing that way. And because you get this, remember the current, the quantum mechanical current, we've written expressions that would look Vg times mod psi k squared, right? We have done that earlier. If you have many k states, you can sum it over many k states, but for a single state, it's just, you can substitute these things. What I wanted to point out is because the wave function now is mod c of x squared, there's a L here, and there's a block function uk squared. This is the total wave function. And group velocity is h bar k over mass, effective mass, right? But for a parabolic band. But the thing is, the k is changing with x. So it's variable, right? K is changing because the electron has more kinetic energy as it's moving to the right. And then so that's your group velocity. That's your wave function squared, q GSGB over L, and the L and this will go away with normalization. I'm just kind of doing it in a bit of a hand wavy way now, because what I want to illustrate is C of k squared is a constant squared by k of x from here, and therefore they cancel, and nothing depends on x anymore. So the current is continuous. So that's what's kind of a this picture explains why the current can be continuous even in a quantum mechanical form if you have a variable, smoothly varying potential. So classically, you would imagine that the electron will never come back because it's rolling down the hill, and quantum mechanically, it's the same deal. It's not going to come back if it's rolling, purely just downwards. It's not going to get reflected. But obviously, if I have even a minute sort of a barrier, or even if I have a well like this point changes. You can have reflections now. So, but as long as it's smooth, it's not going to come back. Yeah.
So maybe I'm interpreting this wrong, but does this say that the amplitude of the envelope function decreases as k increases?
The amplitude of the envelope function decreases, meaning from this picture?
Yeah.
As k is increasing, the amplitude of the envelope function is decreasing. Correct. Absolutely.
So that means you have essentially your wave function is shrinking as you're going to
yes.
lower potential.
So right.
You go down the drop, you actually
right.
shrink.
Right. The amplitude is changing as well. Yeah. Except you just have to make sure that that mod psi squared over the whole distance is still 1. So it will decrease though. From that picture, it should decrease.
So that means the electron is more localized in the higher?
And no, because you mean let's see. So C of x is the total wave function is again the block function times. So you're saying as the k is increasing, then is the net probability of finding the electron decreasing on the right side? Okay, that's a good question. So let's see. If I am if the kinetic energy is increasing to the right side, let's look at one extreme case where there's no change, right? In which case the probability is always uniform, right? But the probability still is, basically the k is still in the denominator, it's just a constant, right? And if I look at this picture, qualitatively, I would like to think that the electron, it's more likely to find the electron somewhere on this side. The potential is lower, right? And therefore, the probability, on the other hand, should increase if you look at it that way. Is that correct? Is that what's bothering you?
Yeah, I think that's
Yeah,
what's bothering me.
right. So, all right, let me say, if I have a plane wave, the probability of, let me just say that this C0, right? So if I start out from some point here versus some point there, right? If A is here or A prime is there, then the C, the magnitude is going to be different now, right? But if I choose only one on the left side and say what is my C of x here compared to that, what is C of x compared to that, then the probability of finding the electron mod okay. So that's just going periodic, and that's not changing because the same crystal, the block function, the periodic part is the same. But this function, just to be very clear, when I have transport like this, this state is moving to the right, and its probability is indeed changing in space, and it's a non-equilibrium situation, and then I cannot ensure that the psi of x squared should kind of be conserved over the whole crystal. So let me maybe try to think of it a slightly different way, because as the k increases, the wavelength gets shorter, right? And the question really is whether the amplitude is really decreasing. Really, I'm thinking it should not decrease because the probability of an electron going through should be constant. But looking at this, just the envelope function, it looks like it should, right? Yeah. And now the current is what is really continuous, and the current is indeed carrying the particle across, and it's the current that's continuous. I don't think the probability should, density should be continuous across. So. But let me come back to that. I think this is an interesting question, so I'll come back to that later. Right, let's come back to that. Probably as I go through this picture, it'll come. We'll have to encounter this issue again. All right.
Well, if the current is continuous, but it's moving faster, then there has to be less of the electron there.
That is exactly that's right. So if it is moving faster and you do a measurement within a small window dx here, right, then it's less likely you will find it in that window. So maybe that's one way to look at it. And so in that case, one has to go to the time domain and do this sort of analysis. Let's come back to that. I think we'll address that issue. It's a good question though. Yeah. Okay, so now that's for the situation when you have standard transport across a normal band. Let's look at if I were to confine the electron, so quantum confined structures now. Confinement. So if I want to confine the structure, let's look at the example of first a three-dimensional semiconductor where we write the effective mass equation, and then we write it for a confinement in only one direction and the other two directions are free. So we're going to look at it this way. Here I have a box of semiconductor with let's say x, y, and z. These are my real space axes, and they're obviously periodic crystal of atoms, and then the electron is free to move in all three directions. There's no potential holding it in any direction, except I'm again looking at the conduction band electron in this 3D crystal. Just looking at the conduction band. You can do it for the valence band too. So in that case, my effective mass equation should look, again, I'm going to assume that the conduction band kx, ky, and kz, there can be momentum in all three directions, right? X, Y, and Z. And that is, let's say the band edge of the conduction band, the minimum of the conduction band is at EC, just like this minimum point. This is a function and this is a constant, plus h square. And let's say also that the effective mass is isotropic, meaning whether it goes in kx direction, ky, kz, it's the same effective mass. Curvature is the same. It need not be so, but let's make that assumption. Kx squared plus ky squared plus kz squared. Does that make sense what I'm saying? So in silicon, for example, if you go along the 1, 0, 0 direction, the effective mass is larger than if you go along the perpendicular to that transverse direction. So in which case you must actually have this thing sitting m star xx and yy and all that. So I'm not getting into those complications. Effective mass is indeed a tensor, but let's neglect that for now. So if this is your conduction band, now we are going to apply effective mass theorem again, and again I'm going to replace these three by their d by dx's, d by dy, and d by dz, right? So you just replace those, and what you end up getting now is d2 by dx squared, and the I will give you a -1 plus d2 by dy squared d2 by dz squared, right? Times the c of x, which is the envelope c of x, y, z, which is the envelope function, is equal to e minus ec. I just took the band edge to the right side, mc of x, y, z. It's basically the same equation in a higher dimension, right? And I think it's very easy to see you can how to solve this equation. You just say that c of x, y, z is composed of some function of x, some function of y, separation of variable business, right? So some function of z, and you plug that in, you'll see that maybe you can tell me what will be these functions x, big y, and big z.
Same as in the 1 dimension.
Right. So it will be basically a plane wave, right? It will be a plane wave because it really has decomposed into three equations now: d2 by dx squared minus h bar square by m star c. 2 is c. Let's write it as big X of x is equal to. Do you see? I mean, you can divide off all the other terms and you just get that for one dimension, for example, right? And that has a trivial solution again because we already have found that. That's let me just also normalize it now. 1 over square root of length along the x dimension. So if I have a box of length Lx here, it will be this times e to the power I kx times x, right? Kx is the wave vector in the x direction, and such that h square kx square by twice the effective mass along the conduction band is E minus EC. Something like that, right? In fact, I should really be a little careful. This energy would be composed of three terms. Okay, so if I do this, I will get h squared kx squared by 2m. So let me just write it as E1 for now. So just to be clear. So what I'm trying to really say is the total energy now with all three terms, the x part, the y part, and the z part. So the total wave function or the total envelope function is going to be a product of three functions, which is x part, y part, and z part, plane waves of all three. 1 over square root of Lx, e to the power I kx times x. Okay. 1 over square root of Ly, ky times y, and that for z. And if the L's, if it's a cube, then it's trivial. All the L's are the same. So that's your envelope function. And so this is where it comes from. But once you use it, you should be able to see the picture and just write those things down, right? Because you don't need to solve it all over again. It's just a plane wave in all three directions. If there's no heterostructures, nothing. It's just a plane wave, right? No reflections of waves. And the energy. If this is the one way to solve, the best way to solve, or rather, the only way to solve differential equations, you guess the solution, and let's say we guess this solution. put that in there, you'll get the energy too, right? Because each of these d2 dx square is going to pull out I times kx squared to the front, right? So I get a I kx squared from this term, I get a I ky squared from this term, I get I kz squared from this term, and I get my energy, which is the unknown kinetic energy, from here. And what will be the energy? It will be EC plus 2m star c kx squared plus ky squared plus kz squared, right? I mean, just the potential plus kinetic. But kinetic has 3 components for all 3 directions. Right? So that's your fully solved problem for the 3D effective mass equation. This is the effective mass envelope function, and here's the energy term now. So you solve the problem for 3-dimensional crystal. And this is not terribly interesting because we have not yet applied this. You already had it, a block picture. You don't even need to write this. But this way of thinking now is very important because I'm going to change this into a heterostructure, and you'll see by just tweaking this, I can recover all the energies and eigenfunctions, without much change. So, yeah. Yeah.
So is there any significance to the fact that the energies that we found are just the EC of kx, ky, kz? Or are you just rewriting?
Sorry. Say that again. I should write it as EX here. Right?
Conduction band is
yeah.
EC plus h bar squared over 2 m star c, that equation. So
yeah.
Then you wrote that the energies that we obtained after solving the entire Schrodinger equation was just that.
No. So what I was good point. So what I was trying to say is, so this is the effective mass equation. If I can solve it, I can get both this and this. Right? These are the 2 unknowns in the equation, right? I'm saying that by looking at the equation, you realize that this must be the solution, or you guess it, or whichever. This is the solution for the wave function. And when you plug that back in here, you get that. Those are the energies. Right? Because you get E minus EC is equal to this whole thing on the left side now. Does that make sense? And because d by dx squared is going to pull I kx whole squared, which is minus kx squared, right? And it will multiply with minus, you get h squared kx squared by twice mass, right? And so you get the first term, then you get the second term, the third term, right? From x, y, and z. So you actually obtain this as a solution. We didn't start out with that solution. We said this is from this effective mass picture. You have to solve the differential equation, but this is an easy equation, so you kind of already know the solution. Now we'll go into a situation where it's a little trickier. Is that clear? I mean, I just want to make sure that, right. All right. So now what I'm going to do is, instead of having the electron be free in all 3 directions, I now put in a very thin quantum well in this structure. And physically, what does that mean? It means that I'm going to have let's say a few nanometers, 2 or 3 nanometers of another semiconductor in this crystal, which has, so this region has a band gap that is, say, large, maybe, so A, B, and A. So A has conduction band edge like here, valence band is over here, but B has a smaller band gap, something like that. Right? So that's A, that's B. And you go back to A again, EV and EC. So now your conduction band profile looks something like this, right? And valence band looks something like that. Does that make sense? So this is essentially, I'm going this way, and this is, right? So now we can ask what are the energies allowed for the conduction band electron now? Because now you have a little quantum well now. This is the quantum well. It doesn't have to be quantized. It can be any dimension. It can be a micron too. But things will change now. So that's kind of what we're trying to say. Okay, so now if you look at this problem, I want to say that every problem of this nature, be it this is where electrons are still free to move in the x and y plane. There are no potential barriers in the xy plane. You can see that, right? The only thing that's changing is if it tries to move in the z direction, that if the electron has any momentum in the z direction, it experiences this change, delta EC, or this is what we call the band offset, delta EC, conduction band of A minus conduction band of B. And this is fixed by materials. If you choose gallium arsenide and aluminum gallium arsenide, you kind of fix that based on the material choices here. So if it has a component of momentum in the z direction, then it experiences it. If it doesn't have a component of momentum, if it's moving purely in this plane, xy plane, it never sees this, right? So the first thing I would do to solve this problem is, again, make use of what I've already done. So what should the envelope function be in the xy plane here? Right? It should be exactly the same. There's no difference, right? So the x part and the y part do not change, right? But the z part must change now, because it's that's the only place where you have a change in the potential, right? If it's going in the z direction. And qualitatively, you can think that if I have such a situation, and if the electron is going at energies like this, here at this energy, it will see very little change, right? But now the new thing is there may be some energies allowed here and here, right? Inside the well, right? And then these are the bound states. If the electron is here, it's bound on both sides. There's a wall on both sides, right? So this is called a bound state, and that's called an extended state, right? And both of them should occur. Right? Extended states should be there, and bound states should also be there. Right? Does that make sense? Okay, now for the bound states, so first of all, qualitatively for the extended states, you can see that it will be now composed because there will be some finite reflection because of this abrupt drop here. There's some finite reflection. And therefore, there will be a few k states. So this k will get, the state at this energy will have not just that k, but maybe one or two more other k's now. Right? Because there must be also a minus k, which is the reflection part of it, right? Which wasn't there earlier. But for the bound states, one way to look at it, and this is kind of easy way to look at it, is a bound state in a quantum well is composed of two states, one going to the right and the other to the left, and they have formed a standing wave. So that's really a bound state, right? So classical picture of a bound state, this is, you may need this idea in solving that problem of tunneling escape in your current assignment. So if I have a bound state inside a quantum well, and these are extended states, and this is the bound state. So I can think of this as, let's think of it as a wave function. The wave function will kind of do something like that, right? Wave function will do something like that. If this is the energy and this is the potential minimum, then it still has what looks like a net kinetic energy. It's not, except so in this region, you still have an oscillatory function, so it's a sine or a cosine sort of wave function. Except here, your energy has gone below the potential barrier, right? So the k has become imaginary now. Does that make sense? Here, E minus EC is positive, but here, at this point, the E minus EC is negative, right? So, and square root of negative is imaginary. So the k has become imaginary here. It has become imaginary here. This is just the evanescent state. The wave is, decaying. So here, your functions will look like e to the power minus, some kappa x. It will look like e to the power plus some kappa x. And here it will look like, a sine kx plus b cosine kx. And you can match the boundary conditions. The wave function should be continuous. There's a little bit of trick in the effective. If the effective masses are different across the junction, then the slope. Let me just write down the wave function should be across any junction. Let's say this is x naught. On the right and the left, just to the right and just to the left, there should be the same. Let's say this is A and B and A. So, and in effective mass picture, because the current is continuous, in traditional quantum mechanics, we use the derivative should be continuous because the current is continuous. But in effective mass picture, just to be clear, the expression for current has a mass in the denominator, okay? Times you get this psi star, grad psi minus complex conjugate. So because there's a mass in the denominator, we must, if we have a free electron, the mass is the same everywhere. But in a semiconductor, the effective mass is changing across a abrupt junction. So you must divide by the effective mass on side B and effective mass on side A. So this is just a minor tweak to the boundary conditions that one needs to use to solve this. And I think you will use this for your problem on the quantum. Yeah, there's a question?
Yeah. Should that be cosine kx?
Sorry?
The cosine is at kx?
Kx, yeah. If this is x-axis, so this is cosine kx, yeah. So what I'm trying to get to now is one way to look at this. Let's say cosine kx. Let's say we place the axis at the center. If x is 0 at the center, then it reaches a peak at the middle. So that's cosine. If it was 0 in the middle, it would be sine, right? So a cosine. Let me change it to z because we have quantum confinement along z. So anyway, yeah, we just change all the x variables to z here. So, right. So cosine of kz is we know that it's e to the power ikz plus e to the power minus ikz, right, by 2. You can see that at least, just looking at this picture, it looks like two waves. One is going with a plus kz, the other is going with a minus kz. Right? It's composed of two, right? So one wave moving to the right and one moving to the left, right? And effectively, the kinetic energy of this state is, this h squared, this k squared by twice the effective mass of this region. So if you want to map it to a classical picture, the net kinetic energy of this bound state is, of the order of this h squared, k squared by twice the effective mass of region B, where the k, let me write it as k0, k0, k0. This is the k inside the well. Right? So that's kind of the net effective kinetic energy. And the k must be such that you can match the boundary conditions. Okay? To do that, we can imagine that we have an infinitely high well, just as an approximation. Let's say we have an infinitely tall well, in which case the wave function must go to 0 at two ends. If it's an infinitely tall well, then the v blows up, or there was this term on the left side, it blows up, so the c must go to 0, and in which case you already know your k. It's the half the wavelength of that electron is equal to the quantum well width, which it must fit inside. So what I'm trying to get to is the k naught, which goes in here, is, again, you see why I'm doing this. It's not infinite really, but we can get very close to the exact answer by just making this sort of a analysis. So the k naught is exactly equal to 2 pi by the wavelength, right? And I'm saying that the wavelength of the electron inside in the bound state must be of the order of twice the quantum well width here. Right? So this must be of that order, 2 times the width of the well. Does that make sense? So as a result, I can get right away that the k naught must be of the order of pi over the width of the well, right? And you know that you actually engineer that, and therefore the ground state energy, which is this energy, kinetic energy, if you want to think of it this way, or another way to say it, this is the quantum confinement energy. Because if it was classical, that electron would be sitting right at the bottom of the well. Right? And because it's quantum, it has to fit this wavelength, its minimum energy is a little higher. Right? So that minimum energy ground state is this, and you can see now that it must be a squared by twice the effective mass of that region times this whole squared, right? Pi squared by length of well whole squared. So it's the ground state energy of that quantum well. You can go one step higher, look at the next state, and that will be a function like that. You go higher, it will oscillate. I mean, if it's bound, it will start getting a node, another, 2 nodes, and so on. Right? So this is one way to kind of engineer or also design how much energies are you getting in these structures. The wave function the envelope function now, as I mentioned, for this structure, will be in 2 dimensions. It still is this exponentials, complex exponentials. But in the z direction, it will be this function, whatever be it, cosine, these functions now. Does that make sense now? So for the bound states, it must be one of those, right? Whichever one you choose. For this, there's a, maybe cosine, this will be a sine, and it will oscillate and all that as you go to higher and higher states. So I'm just going to write that first. And I'll write down the exact form here for this particular situation. After normalization and all that, you will get cosine of a quantum number pi over the will width times z. So just with the understanding that, so these are complex exponentials, they go oscillating for all x, but this is only valid between inside the quantum well, only between here and here. Right? It's not cosine as you go outside. Does that make sense what I'm saying? So if I were to do it really exactly, it is cosine if your z is inside here, and it is a complex, it's a decaying exponential if you get outside. So that's really the exact form of the envelope function in the z direction. Right? So yeah.
This is just the solution to the particle in a box, though. So
Exactly right. So just like good point that so this. If you look at what effective mass theorem is doing, it first said that if your electrons are moving in a crystal, it's exactly the same as a free electron, except its mass is different. Right? If you put a donor atom, it's the same as a hydrogen atom, except mass is different, dielectric constant is different. Now what it's saying is, if it's moving in a heterostructure, it's exactly the same as a particle in a box problem. And with just minor tweaks to what is k, which directions it can move in. But the heart of the problem, you have mapped the problem of a semiconductor in a quantized heterostructure to a particle in a box problem. So every heterostructure, be it quantum well, wire, dot, you solve it with a particle in a box problem now. And the nice thing is we already know all solutions to a particle in a box problem, right? So and that's kind of that you map this problem to a solved problem now, and it's done, right? So you kind of look at the formulas in any quantum book, and you can write down now what will be the energies and all that for this now. So as an example, for this particular situation, you can tell me how will the energies look if I have cosine of something like this here. How will the energies look now? So the only thing that will go is the z direction, right? So that goes away. Goes away as in it gets slightly modified. It looks like the energy now is EC plus the ground state, or the first excited state, or the second excited state of the well. So I will write it as n sub z. It's a quantum number. If you're in the ground state, n sub z is 1, nz is 2, 3, and so on. So each of these states here, each of these bound states in the z direction, is going to lead to what you call as a subband. It's not a full band, but it's a subband. And in each of these states, the electron can. So let's say I plot the energies versus kx. So the minimum energy for a 3D structure, for a 3-dimensional semiconductor, energy versus k was such that this was EC, right? That was the minimum energy allowed, right? But the moment I go to this quantum well structure, because you have this quantum confinement here, the minimum energy is slightly different, right? And maybe I'll explain it this way. Let's say I had just B everywhere. I didn't even have A. I just make it very wide. In which case, this would be the conduction band minima of B. That's the minimum energy, and the energies allowed are kx, ky, kz, all look like that. And now I make this very, very thin, maybe a 2D crystal sort of thing. It's very thin. And this confine it, in which case the ground state energy will start increasing as the square of the thickness, right? As you shrink it, the ground state energy goes up as the square of the thickness. Right? Increases very sharply, actually, as you go to very thin regions. And so what we're trying to say is, if I make and I go in and fix a certain thickness, now that the minimum energy allowed now is E0, which is h bar squared pi squared by 2 m star times the well width squared. So it's shifted up now. And then it still can move freely in the x and y direction. There's nothing stopping it from moving freely in the xy direction, in which case the energy in the x direction will still look like a parabola here. Right? And what we're saying is, because of quantum confinement, you push this band up, and the minimum energy is here, and the that's one. What you call it is one subband now. It's not a full band. It's because of quantum confinement in the z direction. You have what we would call as the subband. This is the first subband. Similarly, for nz is equal to 2, you will have another, and so on. So what does that make sense? I mean, the second ground state will be some other state, and so it will shift it, and then this term stays exactly the same again, right? So the curvature stays the same. It's just that the minimum energies shift up based on the quantum confinement, right? If you had, instead of a square well, if you had a harmonic oscillator sort of well, parabolic well, then the separation between them will be always the same. So this is a harmonic oscillator problem where the states, the ground state, first excited state, and the second excited state, they always have same separation. So that's a very unique property of a harmonic oscillator. That's typically not used much in energy band diagrams, but it is going to become important in the next couple of weeks when we look at light, because the potential that electrons see because of light is a harmonic oscillator potential. So we're going to look at that later. But here, this is just the heterostructure, and these are the energies allowed. And as a result, the first subband is here. And if I were to plot the density of states, originally it was a three-dimensional density of states starting at the band edge and increasing. Right? But now what has happened is these energies are not allowed anymore from here to there. Right? So it becomes two-dimensional. This is a two-dimensional electron gas now, if you want to fix it that way. And the density of states of 2D is constant. Right? So for each subband, the density of states is constant. Then you hit another subband, and you get another one of this slice here. So density of states just add if you have more and more bands. So the density of states looks like a staircase function for this structure. Yeah. So let's see. Maybe there are some questions. I can pause for a couple of minutes and discuss this. So what did I do? I started with effective mass equation. We looked at the 3D problem, and we said, it should be complex exponentials, all directions, and energy would be just like a free electron in all directions, but with a slightly modified effective mass. Now you add quantum confinement in one direction, and in that direction, the envelope function becomes bound state functions. And therefore, the energies for that direction in which you quantize becomes a bound state. It has no k, effectively. It doesn't have a free k. This is a free k, e to the power k. It can have any k, 0 to infinity, effectively, right? But here, it can only have 2 in this state. In the ground state, it can only have 2, right? And in the first excited state, it can, again, have slightly different and all that. So you kind of have restricted k's now, not all k's. That's what we mean by quantum confinement. You select out only a few of the subset. Yeah, good question.
So the subband is simply just the EMZ term.
Correct. The subband is the name of this entire. So let me just say, so this entire energy band, the way I'm plotting here is only with kx, but remember in this particular example, there's also ky. So it's really a paraboloid, if you might. So and so that's the first subband, and that's the second subband. So this energy is not allowed anymore. So these energies are not allowed anymore. For this heterostructure now. Yeah, because even if your kx, this is a good example. So if my electron was moving, so it's free to move in x and y plane, right? But let's say it's not moving, right? It's completely at rest, right? In which case, if it was in a 3D crystal, its energy would be 0, right? Meaning it would be sitting at the band edge, right? But here it can't, because that energy is not allowed anymore. It's sitting, the minimum energy allowed is here now, right? Because it's quantum confined, its wave function cannot match that because of quantum confinement. Therefore, this energy for the quantum well is not allowed anymore. neither is this, neither is this. You basically have created an artificial gap now. And so the band gap, or the conduction band minima, has shifted up till here. And in exactly the same way, if you reflect this around, for the valence band, you'll also have subbands. And so you have the natural band gap of a material of region B, plus quantum confinement energy, plus quantum confinement energy. This is your new band gap now, so of the minimum electron energy here, maximum electron energy in the valence band is here. So this is your artificial band gap now. And you can, for example, if you are going to put electrons in here and holes in here, and they, let's say, recombine to give you a photon, then the energy or the color of that light would be exactly determined by what is this, quantum confinement now, right? So this quantum well thickness will very, you can design the color by changing this thickness now. You can go blue or red based on making it thinner or fatter and all that. Okay, so we'll have a demo of this now. Yeah.
I'm sorry, I just can't read what you wrote underneath there. Just where your hand was?
Here?
B, yeah, where does that start? Because part of it's old.
I see, yeah. Let me fix that. So the effective mass, so this is a continuity equation. So this is the matching condition for the derivative of wave functions, and this is the matching condition for just the wave function across any heterojunction. So compound semiconductors, material A, material B, or any heterojunction. So what I was trying to get to is, in traditional quantum mechanics books, you will not see this term because they're not talking about semiconductors or with different effective masses across the junction. So this is something that comes about. Yeah.
You said we could tune the wavelength of the light emitted, and that's true if it's jumping from the valence band to the conduction band, but now we have these bands that are modified by the quantum well.
Mm-hmm.
But now doesn't it also have the possibility to jump between the first subband and the second subband?
Very good point, yeah. And I will come to that at some point in this class. So what John, you are asking is, clearly I can put an electron here and empty out this state, which is a hole, and then I can recombine here to emit a photon. But what if I have an electron here and I have nothing here, right? Within the same conduction band, can it do the recombination? And the answer is for certain subbands, and we'll see that later. This is called an inter-subband transition, as opposed to an interband transition, going from conduction to valence. This is allowed for as long as you have certain, you meet certain criteria, because the photon takes away with it angular momentum of h bar. So the initial state angular momentum minus the final state angular momentum must also be h bar to conserve it, and that leads to certain selection rules. So not, for example, you will be able to transition from, say, 2 to 1, but not from 3 to 1, and things like that. So only odds or evens will do that. So we'll see that later, but it's allowed, and that's the basis for a quantum cascade laser. It's a unipolar laser where you just kind of push in electrons and it cascades, and every cascade is emitting a photon. So and then you build a population inversion using that. So right. Okay. So before we
Why wouldn't an indirect gap semiconductor then be more efficient at producing light? Because you need to change momentum, and then for an indirect, you just have that built in. So why wouldn't that be more effective, or is it more effective?
Yeah, so the indirect, we'll come to this when we talk about light-matter interaction in more detail. But then the indirect band gap semiconductor, the K state of the electron in the conduction band is here, valence band would be here, and you would have, the photon has very little momentum compared to the crystal momentum, so it really is very difficult for it to match. So people have thought about very clever ideas to break this problem by quantum confinement and all, but it's never really succeeded. So just one more point I want to add here is, you can see that by just extending this idea to, we confine the electrons in one direction in this problem, but let's say instead of doing the whole thin layer over the whole crystal, I had just a very thin region which was extended in one direction but not in the other two. right? So I had, say, a narrow bandgap material B and a wide bandgap material A, like that, right? So in which case, now the electron would be free to move only in one direction, but not in the other two, right? It's confined in two directions. So that is a quantum wire now, right? It can only go in one direction. And in which case now, gradually, you can see you will now take away this term, right? That will become quantum confined, and you'll have left with only one free degree of motion, right? And so your energy will just have kx squared plus, and maybe you confine along the y direction, you will have another quantum number. So you kind of start changing this, right? And you have only 1 degree of freedom. And the density of states for that will look like a 1D structure. Now it will look like that. So you change that. So finally, you can go in and confine it in all three directions and make it into a box, right? And in which case now, the electron cannot move freely in any direction, right? So it's confined in all three directions. It has to match boundary conditions that way, and this way, x, y, and z. It must match boundary conditions in all three directions. In which case now your energy, let me write this one down, is EC plus En along z plus n along y plus En along x. And there's no k left. It's not free to move in any direction. It cannot have free momentum in any direction. And these expressions for a particle in a box problem, for the ground state, you can just use this, right, for the ground state. And you get a very simple expression that it will be h squared by twice effective mass of conduction band of that region times Lx squared, Ly squared plus Lz squared, right? So this is kind of the ground state, and you can have higher states and all that. So this is your energy of the conduction band states in a quantum dot. This three-dimensional confinement, so it's an artificial atom now. You are precisely designed its energy, and there's only one energy at that state. So your density of states for a quantum dot would look, there's one state here, maybe another state here, and there's nothing in between. So only when you have free motion in some direction, you can have a continuous DOS. You have continuous DOS, which is non-zero. If the moment you go to confinement in all three directions, that thing looks like an atom, which is not a continuous density of states. It's discrete energies now. Yeah.
So that's going to have less effect now because not very few electrons can occupy any of those bound states if it's really an atom-like.
Absolutely. So you're saying that the total number of if I integrate the density of states, that's very low. If I have only one dot, it's extremely low. It's like 1 compared to 10 to the power 23. Absolutely right. So whenever we use quantum dots, we have a huge number of them in parallel and all that. So right. Yeah. I mean, so the total density of states really depends on the total number of these quantum dots too. So yeah. Okay. So what we'll do for the rest of the class today is do a demonstration of this quantum well picture, and let me just give a very how this is designed. And we'll do a quick. Oh, by the way, was there a question, Jay? Yeah.
The pi squared disappeared or something?
It disappeared because I wrote it, I think. So yeah, I did not write it. Yeah. So yeah, it should be there. Yeah. So these are worked out in detail in your handout. So please, work through that. And just want to kind of convey the major ideas here. So what we'll do now is. Look at an actual example of this. Screen down. Screen. Let's see, Vlad, if you want to set this up, we'll. So what this experiment? I'll just describe it first. So Dr. Henrik Tursky here, what he has done is he has grown certain structures with quantum wells, and while they kind of bring it back up, I'll just try to tell you exactly what they have done. They have chosen semiconductors. One is a gallium nitride semiconductor with a band gap of 3.4 electron volt, and then what he wants to do is create a quantum well, and wants to design using gallium nitride a laser structure or a light emitting structure that emits in the blue wavelength. So he wants to make a blue laser. That's what he really wants to make. So as a result, you kind of go down here and choose. You can see that you can add some indium to gallium nitride and get close to blue. And that would be kind of the bulk, large band gap, of the material. But typically, what's done is if you grow very thick indium gallium nitride of this composition, there is lattice mismatch, so it kind of relaxes, and you don't want to do that, right? So what you do is you kind of go up here, you kind of choose a certain composition of indium, and then you play the game of quantum confinement. You can, because you make it thinner, this will go up. If you make it fatter, it will go down, and so on, because it changes 1/square of this quantum well width. So then you can zoom in and make a design of this. So Henrik designed this structure. The idea would be he would grow a whole structure where on one side he will have a possibility of injecting electrons in the conduction band and dropping them into the well here, and populating the state, electrically injecting it. Similarly, on this side, you'd have holes in the valence band, but no electrons in the conduction band, and you'll inject it and drop it. Your holes go up to the top, and it will populate the ground state of the valence band. And then, when the electron and hole now are confined in in that direction, they're kind of close, and it can cause a transition, and it will emit a blue photon. So that's kind of the idea here. And so the way he actually grew these materials is by molecular beam epitaxy. It's a very well-known technique by now, developed since late 70s and all that. And so we have systems in the Duffield Hall that we use the system to grow with. So instead of one well, to get more light out in a certain way, what you're asking, if you have one well, you'll get a certain number of watts out. If you have 3 wells, you can increase it. If you go too far, you have problems injecting into all wells. So there's a trade-off always. So he has 3 quantum wells of indium gallium nitride buried inside a gallium nitride sort of structure. There are all kinds of slight different tweaks to it. He has cladding layers because he's trying to make a laser. The light, he'll make a waveguide of it and all that. But the basic idea is he has 3 quantum wells. And here he has doping. On the top, it's a magnesium doping to make it p-type. It's acceptors. Right? And we've talked about, when you have acceptor doping, you're going to empty out some valence band states and make holes. You create holes there. And here you have doped gallium nitride with silicon. Silicon replaces gallium. It has one extra electron in the outermost shell. So it is n-type. It has electrons in the conduction band, but no holes in the valence band. So here's your n-type. And you have electrons in the conduction band. On the top is holes in the valence band. And then when he applies a voltage across it, you can actually inject electrons and inject holes. Or in other words, he's injecting current. And electrons flow opposite to the current, and holes flow in the direction of the current, right? So he injects a certain amount of current, and that's how he's injecting electrons and holes into this structure. And so that's the heart of the device, and this device has been fabricated, and it's kind of mounted on this little optical table that Dr. Protasenko has put together with Reith and Henrik. So his quantum well laser is sitting here. It's already grown, and I showed you the cross-section TEM image of all the quantum wells and all that were designed. And they have mounted it here, and now they have connected it to a current source, and they're going to inject current into it, right? And now, so it will emit light, and he's collecting the light. Hopefully, it's going to work in a spectrometer, and you should see the blue laser, hopefully, the light-emitting diode and the laser work. Just to set it up, what do we expect? Here's what you can do by completely a theoretical design. This is a theoretical design that these are all calculations. This is not experiment. You can calculate that at when your zero voltage applied to this diode, your Fermi levels on the both sides are the same. Here's your p-type valence band is close to the Fermi level, right? N-type conduction band is close to the Fermi level. Here's the gap. And you can see all these little tweaks here. These are the quantum wells that kind of go and shrink the gap in this small little regions here, right? And design the color of the light that's going to come out that way. You can see in this whole picture they're very thin, but they're extremely efficient. Basically, as you can imagine, if an electron is going to go across and there is a well, it's a very high chance it's going to drop in the well, especially if it is a quantum well, meaning it has no way to go across it. It has to cross the well, right? It's going to drop. If you have wires or dots, you have a little harder time because you can have paths that you escape, right? In the spatial, you can escape it, but in a well, there's no escape. You can escape if there's a finite probability that the electron will drop into a well or it will go across. So there's a reflection and all that sort of thing. And then we apply the voltage. the difference of the voltage is this, Fermi level difference, just like the Schottky diode. If you remember, the quasi-Fermi level of electrons minus quasi-Fermi level of holes is equal to the applied voltage, Q times V. So at 3 volts, for example, it is like this, and at much larger, maybe 4 volts or so, you get into a situation when the Fermi level here for electrons goes into the conduction band, and the Fermi level for holes goes into the valence band, and that's what's called population inversion. So in the conduction band, you have a lot of electrons, and the valence band, you have a lot of holes. That's opposite of what nature wants. Nature wants valence band to be occupied and conduction band to be empty, and you have inverted this natural situation. So that's population inversion, and that's where you get lasing and stimulated emission and all that. Okay, so the current will look like very, very low initially when you have this, because the electrons have to go over this whole barrier. Holes have to go over this big barrier, right? So the current is low. And then you apply a voltage, and around the band gap, just around the band gap, you can see the current will pick up, right? And then initially it will operate without population inversion, so it's going to just emit light. It's a light emitting diode, it's a LED, right? And then once it reaches a population inversion threshold, it's going to start lasing. It becomes a laser. Then it has stimulated emission. Okay, so let's see. Hopefully you can make it work. And yeah. Oh, I can. Should I remove this?
Oh, it does.
Right. Oh, good. So.
We just need to readjust the spectrometer. Fiber.
Just put it in here, just we bumped over a couple of times.
Oh, you bumped it on the way?
It's not bumped, but I'm driving forward. Can you see it?
They're just setting it up now. So
Constant power, not the pulse one. You just need to, just click.
So while they're doing it, so this is the spectrometer. It's measuring photons at what wavelength. Here's the wavelength. You can see it's 400. Yeah, you can see the 470. I don't know, maybe some 460 nanometer. That's blue, and you will see it with your eyes sometime. Hopefully, once it starts lasing, it's really bright blue color. So that's blue, and that's been designed with this quantum well structure. The blue color of it. Yeah, and at this point, it's a light emitting diode. It's broad, so there's no lasing yet. So yeah. Oh. So this is the spectrometer of photon, and this is the IV curve, current versus voltage, current, and this is voltage. And once they start operating it, you'll see that it will be very low, and then when you reach the band gap, it will start increasing for the PN diode, and you'll see the light emission. Yeah?
Why do we see 2 peaks in the spectrum? When it was there, it was like a little drop.
Good point. So actually, the quantum wells have many states in them, and you can have transitions between the ground state to valence band or the first excited state to valence band. You can see all of that in this. As electrons transition from top to bottom, you can see all of those things. Actually, yeah. Or if you have quantum wells of slightly different thickness, you will see different, so there are, one peak because of one well, the other peak for another well because the band gaps are slightly different depending on the thicknesses. So you can design it in that way too. Yeah.
Yeah, could it also be spontaneous emission?
This is currently all spontaneous emission. So because at this point they're injecting I don't know how much current, you are not above the threshold of the laser yet. We'll cover that part in the later courses, but yeah, this is spontaneous. There's no stimulated yet. Only when you exceed a certain injection current, it will go into stimulated. Yeah.
So the spot is holding something like 1 microsecond.
Okay. So.
Otherwise, it will be like when it starts lasing. This is huge integration time.
So one of the big, while he's setting it, one of the big problems with lasers is it is extremely efficient in converting light, but you have to cross a very big threshold. So there is a lot of heat dissipation. If you're not careful, you can easily burn it and all that sort of thing. So
So first we want to sweep like from.
yeah, let's do a IV curve from low to maybe 6-7 volts. Yeah. So now he's starting out a current versus voltage sweep. Currents are very low now, and once it reaches the gap, you will see it will exponentially increase. It's very similar to the Schottky diode, except this is GaN, so the gap would be about 3.4. Yeah, there you go. Let's see. And not much light, or what's going on? Oh, there you see. It's starting to pick up now. This is spontaneous emission at this point. And if you were on my side, you would see it with your eyes. It's just oh, you can see that blue spot there. They've kind of tried to create this line.
Yeah, this is when it's spontaneous emission as well.
I think that putting a white.
Oh, there's
over
better.
here is
Yeah.
better.
So this is what you're seeing is the pattern. Okay, it's off now. The
Maybe just well, you can go like 4,000 points.
Yes, yeah, we can go like 4,000, I guess, and
Go
4,000. No, there's a 1,000 limit, I think.
all right.
1,000 is the problem. We need to increase the compliance.
Oh, to go to lasing.
Okay, so actually, I think that we can stop it now. Hmm? Oh yeah, this one also. Sorry.
If you actually make the laser, you don't want to burn it out. I think so. Henrik has to be very careful. Yeah.
Yeah, but I did change that one.
Okay.
There's like, you have to change it in 2 places. So actually, I think that those peaks that are appearing in the spectra that you can see are due to the cavity, not due to the differences in.
Oh, good point. Okay, right. So while it's picking up, so you're asking about the multiple peaks. So because this is a laser cavity, it also has Fabry-Perot oscillations for the light. So you will also see peaks because of that. But yeah. Okay, this is slow scan, right?
Yeah,
Which is
sorry.
fine, which is fine.
Actually, I could.
No, it's all
Let
right.
me do that. I'll just start like
All right.
probably like 4 volts or something, then
All right.
we'll save time when nothing happens.
Sure. Okay, there you go. Actually, right, I just forgot for a second. So if you measure these peaks, this is also a sensitive measure of the size of the cavity in which the material is, because these are very sharp Fabry-Perot. So yeah. So okay, very faint starting out.
So which I going to do the laser?
Yeah, let's try. Yes, so to get that we not to burn the laser and to make it laze, we actually need a pulse mode for that. So we're going to use 100 milliseconds here. And, so like 100 seconds. It's no. Oh, sorry. Yeah. I'll change the things.
That's just to avoid too much heating. You just have pulsed injection rather than direct, continuous wave.
So what we should see is when it starts to laze, actually all the current that we are putting into the structure is converted into light. So there should be like a lot of light at that time. It will blink.
Mm-hmm. All right.
We are not there yet.
It's still faint. It will be hopefully pretty bright. Yeah.
Yeah, you can see that now.
So this really spectrum narrows very much. You can't see it because it's way out high. We're very sharp. And this is beautiful.
There's a really huge difference between an LED and a laser.
Yes.
Based on integration time, it's like 5 orders. Because just to see the same thing, we have to go like 1 microsecond integration time. Maybe if you go just one more time, just to see.
Yeah, we can.
Yeah, go to the, and maybe like from 6 volts till.
So the blue laser became possible only in late 90s. So it's the newest optical photonic device that.
Yeah, microsecond. Yep. Yes.
All right. Wait. So while you're setting up, so also the diode itself is extremely useful. Oh, it's already lasing.
Yeah, it's lasing, but
What?
we still cannot actually measure it.
Yeah, it's
It's
still-
too bright.
Oops. Okay. Yeah.
Oh,
Oh, now it's doing.
sorry.
It really is. Looks like it's narrowing. So the laser is the most efficient way to convert electrical energy to light. The most efficient, much more than the LED, and especially if you have a lot of electrical energy and convert into light, you can reach efficiencies close to, I don't know, 60-70% almost of conversion efficiency. It's amazing actually what it can do. So.
That's came from like lower voltage from spontaneous.
The problem is that I cannot change the integration time.
This is 1 microsecond. I think it's.
Okay.
So are you guys trying to change from what, spontaneous to stimulated?
We just wanted to measure the peak, but
You want to see the peak, right? Okay, it's all right.
not to oversaturate.
Yeah. Andrew?
Just had a question about something I saw in the design. So on the top contact, you have another heterojunction between InGaN and gallium arsenide.
And GaN, yeah.
Is that just to make the ohmic contact with the metal, or?
So I think there are two things. One is for good electrical contact, but also a lot of waveguides. So you need to confine the optical mode within the. So the blue wavelength has a certain. It has a certain wavelength inside the material, and the light has to be guided and made incident of the two mirrors. So the refractive index of these materials also changes when you make heterostructures. So using the refractive index, you can make waveguides, and so there's also that aspect of this that he has taken into account in this design when he grows the material for waveguiding. So that's the photon design, and we talked till now only about the electronic design. And, yeah. Okay, good. So I think it always saturates. So you need a better spectrometer to measure. Yeah. Okay. Okay, thank you guys. I think it's very, I always feel excited about this stuff. So. Okay. And if you have any questions for them, please feel free.